Welcome back. As we continue with chapter 14 on solutions, let's review what we have done so far up to a part. So you have a solver, right? Which is what we have in here, which you can see that is a lot more of what you're trying to dissolve. So the solvent is on the one on the highest quantity. The solute, what you're trying to dissolve, is on the lower quantity. So if you mix it with the solvent and you come out with a homogeneous mixture, then you have a solution. If you come out with a heterogeneous mixture, then we don't have a solution. So this chapter we're dealing with solutions, and we saw how this solute solvent interaction is strong than the solute-solute interaction in terms of intermolecular forces, and that's what causes the formation of the solution. And we also saw that it's also determined by the energetics of the solution. So separating the solid from the solute requires so much energy. That's the enthalpy of the solute. Separating the solvent from the solvent so it can enwrap the solute also requires energy. And when they come together, we call that the energy of mixing, which is tend to release energy. And we also saw that the enthalpy of the solvent plus the enthalpy of the mixing is what we call the enthalpy of hydration. And we saw that the enthalpy of the solute is the opposite as the energy of lattice. The energy that keeps the solid together is the opposite of the energy required to break it apart. And all those two combines, the enthalpy of the solute and the enthalpy of hydration, is what gives us the total energy of the solution. And for a solution to form, it would require the enthalpy to be exothermic, but we have evidence that some solutions are endothermic, which means there gotta be something else. And this something else is the entropy, which is the tendency of the universe toward disorder. So if you ever have a solution process in which the process results to be endothermic, it's because the entropy is the determining factor. And I promise you that when we make it to around chapter 17, we will see that the gift-free energy is really what determines if something is going to happen or not. And that's going to depend on the enthalpy and the entropy. But more about that later. So that's kind of a quick review of what we did last time. And that's what we just finished. So new concept. Describe the effect of temperature on the solubility of solid and gases in liquids. So temperature is a measure of energy, kinetic energy for the most part, or which is a reflection of the heat. And we know that the formation of the solution is going to depend on the enthalpy of the solute, which is separating the solid from the solute. So if we have a solid, where the particles are very close together, we're going to need energy to get them to move apart from each other and separate them. And that would be a solid. But what happens when the solution forms? When the solution forms, all these solute particles are encased in the hydration cages. So in terms of temperature, separating these particles allows for the solvent to get to them better and do the hydration cages, so that keeps them hydrated and keeps them in solution. So it allows for the solid to dissolve better due to the more movement. What about gases? Well, gases are going to be a little bit different. Because if you have a solvent and you try to put a gas on it, the gas, as we know, is moving a lot faster. So it's at the same time you're increasing the temperature, that's gonna even increase the speed of the gas more, and that will cause more of them to escape. So when you're making a solution, if the temperature is high, more molecules of the gas will tend to escape because they're always moving randomly. And if they happen to be heading upwards, they will escape the solution. So that's what, if you have a soda drink and you don't want it to go flat, you try to keep it on the refrigerator so the soda doesn't escape. The carbonate doesn't escape. And here's an example of how solubility is affected in solids with temperature. And we're going to follow potassium nitrate. So you learn on Chem 1411 that compounds with ionic compounds with nitrates, they're always soluble. But on 1411, we were kind of naive because you cannot say that something is always soluble. You can talk in terms of being more soluble or less soluble. For example, if the temperature happens to be 0, you can dissolve up till about 12 grams of potassium nitrate in 100 grams of water. But if you were to increase the temperature to 30, let's say, on that case, then you can dissolve around 65 grams of potassium nitrate in the same amount of water. So as the temperature increases, solids tend to dissolve better. And that's what you see potassium nitrate, the graph is increasing. The same with lead nitrate, the same with calcium chloride, the same with sodium nitrate, the same with potassium chloride, the same with potassium dichromate, the same with potassium chromate. The only exceptions we see is this compound, cesium sulfate. And most likely is because of the way the lattice is constructed. So in general, so we cannot say always, in general, solids will tend to increase solubility as the temperature increases. And we already saw it's because the particles of the solids will move faster now. They will lose the alignment that they need for the intermolecular forces to hold, and they will start separating. Once they separate, the solvent can surround. Once they start separating, the solvent can pull on them better and surround them better. So solids solubility tend to increase with temperature. So let's try this concept. Let's make sure we understand it. So the question was, draw beakers showing 45 grams of potassium nitrate mixing with water. So we have 45 grams of potassium nitrate, and we're gonna mix it with water, just like the drawing is showing. And we have 100 grams of water, which goes hand in hand with the graph that we're using. Usually solubility is usually given by 100 grams of water, grams of the solvent. So I want you to draw 2 beakers, both of them with 45 grams of potassium nitrate, mixed with 100 grams of water, one of them at 40 degrees Celsius, the other one at 0 degrees Celsius. So at 40 degrees Celsius, how do we use that? Well, we go to the graph. At 40 degrees Celsius, we're gonna see what happens with the solubility of potassium nitrate. So at 40 degrees Celsius, the solubility of potassium nitrate It's going to be how much? It's going to be around 61 grams. So 61 grams of potassium nitrate can be dissolved in 100 grams of water. So if I'm trying to dissolve 45 grams, and at that temperature I can dissolve a maximum of 61, then you will get a homogeneous mixture because everything has been dissolved in the water. What about at 0 degrees Celsius? Well, at 0 degrees Celsius, we're gonna go there and we're gonna see that potassium nitrate is right there, which is gonna be around, I would say, let's see, I would say about 13 grams. And you don't have to be precise, you just have to demonstrate that you know how to use the graph. So around 13 grams of potassium nitrate will dissolve in 100 grams of water at 0 degrees Celsius. That means that out of 45, only 13 will dissolve, which leave us with 32 grams undissolved. So the way I will draw this will be, so one of the potassium nitrate didn't dissolve, which means it's going to go to the bottom, and that's going to be exactly, based on my measurement from the graph, 32 grams. Everything else is dissolved in water. So everything else is potassium nitrate aqueous. Potassium nitrate aqueous. Because it's dissolved in water. So that's how you can show that, yeah, you know how to use this type of graph, and you understand what dissolve means. Out of 45 at 0 degrees, only 13 can dissolve, so everything else is not going to dissolve. So this is your daily work 14.3. And make sure that on your daily work paper, you always label them. And remember, I am grading for completion, but I always checking to see if you have any problems that I need to address. So even if you get 100, see if I left a comment for you. So what about the solubility of gases versus solids? And we covered this already at the beginning. So once more, let's say I have a 2 liters soda drink, and it's open, and you have your drink in there, and you have the same bottle. Imagine it's the same bottle with the same amount, also open, and this one is placed on top of a bunch of ice. And this one is placed on a hot plate at a very low setting. You have the molecules of the gas dissolved in the solvent. So which one are moving faster? The one on the ice or the ones on the hot plate? Obviously, they're always moving, but these ones are moving faster. Sorry for that. And they're moving randomly. But if they happen to be moving upward, they will escape faster than the ones that are moving slower. Therefore, less of them are going to be part of the solution, which means solubility in gases, so gases dissolved in a solvent, decreases with an increase in temperature, contrary to the solids. So keep that in mind. And here's your daily work 14.4. Imagine you have a soda drink and somehow you are drinking it at Mars, where the atmospheric pressure is less than 1 atmosphere. Would your soda go flat, faster, or slower than at Earth? I know we didn't talk about pressure, but you learn on 1411 enough to answer this question. So going flat means that gas molecules are escaping from the solution. How can you relate that to the solubility of CO2 in the soda? That's what you are doing. How will this solubility be affected if there is a sudden increase of temperature? And that's the new material now. And that will take care of understanding how temperature affects the solubility of both the solids and the gases. And remember, nothing is absolute. We saw a solid that solubility decreases with temperature, but those are the exceptions. So at this point, we can say that we have finished 3 of our first objectives. We understand how the intermolecular forces affect solubility. Remember, attraction between solid-solid versus attraction between solute-solvent, right? And we saw that the polarity have a big effect on that, because when the intermolecular forces are similar, they will tend to come together. We saw how the enthalpy and the entropy affect how a solid goes into a solvent to make a solution. And now we just saw how the temperature affects the solubility of solid and gases. So let's move forward. 2 more concepts. Describe the role of equilibrium in the solution process as it relates and its relationship to solubility of the solid. And equilibrium is nothing more than a process that goes on opposite directions to a point where it reaches a place where it doesn't change anymore. The process continues, but you don't see any effect on change, because for every, product that is formed, reactants are formed. So once you get to that point, it remains constant. Describe the relationship between partial pressure of a gas and its solubility. So to understand partial pressure, we have to understand equilibrium. So let's say you have a container where you have a liquid, which is a solution that contains a gas. So we study vapor pressure on chapter 12 for a substance, a pure substance. Now this is a mixture. This is a homogeneous mixture, a solution, right? So now we're talking about what happens to the solute, in this case the gas, in terms of the partial pressure. Why do we call it partial pressure? Because molecules of the solute are going to escape. Molecules of the solvent can also escape. So we're only talking about the pressure of the solute. So we're not talking about the total pressure. We're just talking about the partial pressure. Only one part of the mixture. But both of them are producing gaseous substances, because as you know, water is always producing vapors. Doesn't matter what temperature. So in terms of the solid, in this case the gas, molecules are moving the molecules are moving randomly once more, and the ones that are pointing upward will escape, and once they escape, they continue moving randomly, and if they happen to come down, they're gonna put pressure on it. So that will be your partial pressure, because it's only based on one component out of 2 components. So as a molecule comes in, one can go out. So that process is going to continue back and forward until an equilibrium is established. When an equilibrium is established, then we can be talking about vapor pressure. So that's what we have to understand, the equilibrium process in terms of establishing a non-changing vapor pressure, as long as the temperature remains the same. So let's see how we can visualize this on a problem. So we have an equation, we call it the Henry's law, that tells us this is how much is gonna be dissolved. And I'm gonna be measuring that on molarity. And you know that molarity is the amount of moles per liters. So if I have a gas, for every 1 liter of gas, how many moles of the gas are part of the solution? And for every substance, since every substance can exhibit different intermolecular forces, there's a constant for that substance. And we get that through experiment. For example, and it's basically telling you the molarity that is going to stay in solution based on the pressure. So the units are given molarity by pressure, atmospheres. For oxygen, is 1.3 10 to the minus 3. So 1.3 10 to the minus 3 mole for every 1 atmosphere. For nitrogen, it's smaller. And let's analyze this. Let's say, so this is happening in water. So if I have oxygen surrounded by water, compare to nitrogen surrounded by water, because we're talking about solubility, right? It's telling me that it's going to be easier for the water to retain the oxygen. So the amount of oxygen in the water is going to be bigger than the amount of nitrogen in the water. And the question could be, why would that be? Why would the oxygen be retained in water better than the nitrogen? And for that, you have to go back to the beginning of this course. You gotta go back to intermolecular forces. Oxygen, Lewis structure. We can see that it's a symmetrical molecule, therefore non-polar. Nitrogen, Lewis structure. You can also see that it's a non-polar molecule. So the interaction with the water for both of them is only dispersion forces. So which one have a stronger attraction for water? It's going to have to be, since both of them only have dispersion force, it's going to have to be the one with the bigger mass. 32 grams per mole. Sorry for that. For every 30 grams per mole. Sorry, 28 grams per mole. The nitrogen is 14 grams per mole each. So since oxygen have a bigger molar mass, it's gonna exhibit a stronger dispersion force. So that's why it can grab to the water better, and it can be retained by the water. Therefore, the solubility, which is how many molecules are captured by the water, is gonna be higher. So we can make sense of these tables. We can make sense of these numbers with the basic knowledge that we have from intermolecular forces. So that's where these numbers are coming from. So once more, the Henry law tells us this is how much is going to stay on the solvent or on the water for most of the, based on this table of the solute. Each substance is going to have its own unique value for the Henry's constant. And then this is going to be the value of the vapor pressure. So when I have a solution that contains a gas, the amount that it's retained on the solvent is going to be given by molarity. Some of them are going to escape. and they're going to put pressure in there. So once an equilibrium is established and the amount of molecules of the gas on the solution reaches an equilibrium with the amount of molecule gas on the gas phase, then we're going to be able to measure the vapor pressure. But this vapor pressure only deals with the solid, doesn't deal with the whole solution, so it's a partial pressure, and that's the pressure that it goes there. So it's very important for me that you just don't plug numbers on this formula, but that you understand the chemical concepts involved with them. That you can do a drawing and really say, oh, this is what's happening. That's what I'm going to be looking for on the test. I care less that you can plug numbers on this formula. But do you understand when you get, this is my S, do you understand? Okay, so yes, this soda will have a better flavor because I'm going to be able to keep more CO2 on the soda. So how do we use this formula then? Use Henry's law, right there, to determine the molar solubility. So solubility is going to be given by molarity. So it's going to be molar solubility. So that's what we're looking for of helium. So we're looking for helium, which is right there. So this is the value we're looking for at the pressure of 1 atmosphere. And my pressure is 1 atmosphere. So once you understand what each symbol represents, you're looking for this given 3.7 10 to the minus 4 molarity over atmospheres. That came from there, right? Multiply by 1 atmosphere. So the pressure has to be on atmospheres for you to do this problem at 25 degrees Celsius. Why? Where do we use the temperature? Nowhere. You just have to make sure that you're using the right table. If this table was at 45 degrees Celsius, you cannot use this table for this problem. So you gotta make sure that the table matches with that. And most of the time it's gonna be 25 because that's the standard for kind of a room temperature. So when you multiply 3.7 10 to the minus 4 times what atmosphere, you're gonna get 3.7 10 to the minus 4 molar, because atmospheres cancel with atmospheres. So it's telling you that for every 1 liter, you're gonna have 3.7 10 to the minus 4 moles of the gas dissolved on it, or 0.0037 moles for every 1 liter of solution. And that's how we use Henry's law. Determine the maximum amount of helium that can dissolve in 250 milliliters. So how do we do that? Well, you already found out. You already know that the molarity equals 3.7 10 to the minus 4 moles for every 1 liter, right? So if I have 250 milliliter, which is the same as 0.250 liters, then all I have to do is multiply that by 0.2500 liters, and that will give me my moles, right? But it's not asking for moles, it's asking for grams. So from Chem 1411, you multiply that number by the molar mass of helium, which is 4 grams for every 1 mole. And that should give you your grams. Make a drawing that clearly represents this situation. So, typical question on one of my tests. Can you show me? Make a drawing that clearly represents this. Well, the drawing can be, I have a solution, I have gas molecules of my solute in there. And I'm gonna try to show off. And I also have my solvent. And my solute is gonna be represented like this. So an equilibrium is gonna be established between the molecules of gas and the molecules of the solution coming in and out. And there's going to be also some molecules of the solvent on the being part of the vapor pressure. And what I'm going to say is that the amount that are dissolved is 3.7 times to the minus 4 molar. I'm going to say that the pressure is 1 atmosphere, and this is happening at 25 degrees Celsius. And that's how you can clearly represent this situation. You talk about the equilibrium, you talk about, you know that the number you get from the Henry's law is how much of the gas is dissolved in molarity units. And you know that the pressure that we're talking about is the pressure that the molecules on the gas phase are putting on the solution. If you can do all that, you understand Henry's law, not just plugging the numbers in there. Here's your daily work. So how would you solve these problems? You got the formula with 3 different variables. Which one is 0.212 molar? Does the temperature goes anywhere? Where do I get my KHP from? And how much is the pressure? That's what you're looking for, right? Well, how much is the pressure? And with that, I would say that we understand how intermolecular force relates to solubility. We understand what that term means. We can talk about the energetics of forming a solution. Now we can see why the equilibrium is so important when we're dealing with gaseous solutions. We see how the temperature affects the solubility differently for the solid and the gas. And we saw how the partial pressure relates to solubility using the Henry's law. And that's it for now. See you soon to continue chapter 14 later. Take care, stay warm, stay safe.